I'd like to tell you more about direct and indirect bandgap semiconductors, specifically focusing on their absorption characteristics. So let's take, for an example, gallium arsenide. It's a direct bandgap semiconductor. And so if I plot the absorption coefficient versus h nu, the photon energy, I'll get something like this, where you can see a very sharp transition. A more illuminating way to plot this is essentially to plot the square of the absorption coefficient versus h nu. And what you see is you actually see a linear characteristic. Now, let's take a case of a more complicated material, germanium. If I plot the absorption versus photon energy, first what I see is I see an indirect bandgap, and then if I raise the photon energy, I see direct bandgap. So here is the direct, and then here is the indirect. Another, perhaps more clear way to plot this is to plot the square root of the absorption coefficient versus h nu. And what do I see? I see something that looks like this. So here, this is the case for high temperatures. And then I can make a similar plot for what happens at low temperatures. So this is what happens at low temperatures. So the question is, what's going on? And in order to understand that, we really need to take a look at mathematically what's happening with the absorption coefficient in terms of the joint density of states for this indirect semiconductor. So let's go ahead and start that discussion. Because the semiconductor is indirect, when I look at the amount of energy that plays into a transition to excite an electron from the valence band to the conduction band, we know that this is equal to the energy of the photon involved, and then plus or minus the energy of the phonon. We can also think about momentum. So h bar k final is the momentum, final momentum of the electron involved. And essentially, this is going to be equal to h bar k sub I, so the initial momentum, and then we have to do plus or minus the momentum of the phonon involved. It's important to note it's plus or minus because essentially we can either have phonon absorption or emission in order to essentially get energy and momentum conservation for this process. Note that the F and the I refer to subscripts denoting the final state and the initial state. So in order to take a deeper look at this, what we have to do is we have to write down the joint density of states. So if we think about the initial density of states, so in the valence band here, this is actually going to be proportional to the initial energy to the 1/2. Now we can talk about what happens in the case of the final state. So this is essentially proportional to EF minus EI to the 1/2. This can be rewritten, and it can be rewritten as h bar omega minus EG minus EI minus plus h bar omega to the 1/2 power. So that's what's going on there. So now what we actually want is we actually want the joint density of states. And so we get that by essentially multiplying these two functions and integrating. So g of e, the resultant thing, is going to be proportional to the integral from 0 to h bar omega minus EG minus plus h bar omega. And then we're going to have a derivative with respect to the initial energy. And then here we have h bar omega minus EG minus EI plus minus h bar omega to the 1/2 times EI to the 1/2. So that's essentially what needs to be integrated. And if we integrate it, what we find is that g of e is proportional to pi over 8. And then here, this is h bar omega minus eg, and then minus plus h bar omega squared. And this is valid for energies where of the photon where h bar omega is greater than or equal to Eg plus or minus h bar capital omega. Okay, so that's actually what's going on. And so now we can take a better look at our graph. So the reason why we have these two slopes in the case of high temperature is in this case, this lower slope corresponds to phonon absorption. And in the case of this upper slope, it corresponds to phonon emission. And in the case of the temperature being low, this corresponds to phonon emission. So hopefully, this gives you a better picture of what's going on. Essentially, what you have to think about is there's a plus and minus in the relationship for the absorption coefficient. So you can either emit a photon or absorb one, depending on what is going on with the temperature of your system.